design, photometric, and it's free. Well, they have a free version, which is this. So please write this address. Is www.visual-3d.com. Okay. So let's see the slides from chapter 4, light sources. They are right here. Hold on, let me get them. And then let me share it with you. Okay, so now where is this? I don't see the not this, we don't want this here. Okay, right now, so here it goes. Can you see that?
Yes, sir.
So this is chapter 4, okay? The primary purpose of the light source is to convert electricity into light energy. How well does the source performs is called the luminous efficacy, expressed in lumens emitted per watt of power consumed. Okay. Now, the perfect source, which converts without loss all the electric energy into a yellow-green light, that efficacy of the perfect source would be 683 lumens per watt. That's the theoretical maximum efficacy of a practical source. No light source presently being manufactured comes close to its theoretical maximum efficacy. Now, in this table, LED lamps are not included because this book is rather old, from 1980 something. So at that time, the LED was already invented, but not used as a light source. Okay. So then here at this stage, the best would be the high pressure sodium lamp. And that's the lamp with the yellow color, okay? And then look at the original incandescent lamp in the year 1879. That was the lamp invented by Thomas Edison. And look how inefficient it was. Okay. A ballast. Okay. So now let's go to the next. The objectives. Different type of light sources. Function. Characteristic and rating. Advantages, disadvantages of each type. General applications of each type. Okay, so then here we have fluorescent lamp. Methods of starting a fluorescent lamp. So you see the lamp in 3 figures. The lamp is not conducting. There is a gas inside. So in order to start the lamp, that gas has to be led into breakdown, electrical breakdown. Okay, so that means producing a discharge. Now, you can see the transformer, which produces high voltage. In all three, produces high voltage needed for the breakdown. Now, in the top, the lamp has 2 pins on each side, 2 pins. In the middle, the lamp has 1 pin, only 1 pin on each side end. And on the bottom, again, the lamp has 2 pins. So when the lamp has 2 pins, that means there is a heater inside the lamp, and that heater emits electrons. So that emission of electrons is going to help the breakdown to have the discharge. Look, in the middle, the instant start, there are no 2 pins, so there is no emission of electrons. So here, the discharge is produced by brute force. Brute force, such a strong voltage there that it breaks down the electrically breaking down. That's what I mean, producing the discharge. Okay. Now the first and third are similar, except that in the first there is a switch which is closed at the beginning so that the current can circulate through the filaments, through the switch, which is closed, again through the filaments, and then close the circuit. And then after the filaments get hot, this switch will open automatically. Okay, in the bottom, there is no such a switch. There are just windings, a few turns at the top for one of the filaments, and a few turns at the bottom for this other filament. Okay, so this is for fluorescent lamp. And then once the discharge is running, we need a choke coil, which is a manner to limit the current, because the you see the electric discharge is it's a nasty element. As a circuit element is going to be non-linear. So if you hit that gas, as it gets hotter, it conducts more easily electricity, and then it can be there can be a runaway discharge, increasing current, getting hotter, increasing current, because the resistance of the lamp diminishes. So then they put a coil to limit the current. They don't put a resistor because the resistor consumes power. They put a coil which consumes only reactive power, but not watts. Okay. The bottom doesn't have a coil, so then the current is limited by the auto transformer. Then we also have capacitors. We can also have capacitors, look, for optional power factor correction. Power factor correction. Capacitors. Okay, let's look at this.
Dr. Ramos.
Yeah.
So for the bottom one, would you like design it with leakage inductance, that transformer?
Yeah, okay, so the transformer is the one that is doing the function of the choke, right?
Yeah. So you would like change like the core geometry or something like that, right?
Well, yeah. I wouldn't be able to discuss right now on the details of the magnetic core. I'm sorry.
Yeah.
Okay, so now this slide is for two lamps. Two lamps, lamp 1 and lamp 2. Rapid start operation. So there are filaments. Okay, so one of the inconveniences of the fluorescent lamp is the stroboscopic effect. That is 60 hertz every 2 times per cycle. So at a frequency of 120 hertz, the current goes through zero. It crosses the zero axis. And then the lamp dampers a little bit, less intensity. So then that variation of intensity, sometimes some people can see it as stroboscopic. So then what they do in lamps is probably the best way would be to use three-phase systems or two-phase systems so that the zero crossings do not occur at the same time. Okay, so then there are two lamps and they don't have synchronous zero crossings. So while one lamp is low, the other is high. So then that get away with the with this effect. Okay, so then we can use three-phase. All right. So especially in commercial application or industrial applications, such as here in the university, where we have a lot of lamps in every room, classroom, etc., etc. And the distribution voltage for that is 480 volts, three-phase. Three-phase. Now, every lamp is fed with line to neutral voltage, which is 480 divided by a square root of 3, which is 277 volts. Okay, so then, and then we have in a given fixture, we may have 2 or 3 lamps, and that's how they function, okay? Now, the special are called mercury lamps, all right? So high intensity, there is this kind of high intensity lamps, HID. So those are the lamps used in public outdoor spaces, such as parking lots, streets. So then those lamps are powerful. Okay, they need a power factor correction. So it started in the 1940s with mercury, nice color, white. Later on, sodium, horrible color, yellow, most efficient. Then later on, back again to white, metal halides. See, so let's see if they are shown here. Let me go back to the first. Here, look. So look, metal halide, 75%. No, lumens per watt. High pressure sodium lamp, 110. The mercury lamp, the first lamp, is 400 watts. So that's why they call high intensity discharge lamp. They are very hot. They run very hot. Okay. Because look at the amount of wattage. Okay. So here we have the three types. And nowadays, what we are seeing is LED moving on this. Let me see if I get some information about LEDs, at least the trends, and if I can get the book. I didn't find the book. I have a book on LEDs, so okay. So let's go back here. That's the high intensity lamp. Okay, so then here are summaries, incandescent lamps, advantages. Simple, no ballast required. So remember, the fluorescent and the high intensity discharge lamps, they need ballasts. So because they are, they need to make a discharge in the gas. Okay, so the incandescent doesn't need a ballast. Also, dimming, they are very simple to dim because the incandescent basically is just a resistor. Okay, so if you put down the voltage, you can dim. In the other, you need to be more careful because if you put down the voltage, you may turn off the lamp. Turn off the lamp because that's a discharge through a gas. Okay. Also, the color of the incandescent is more similar to the natural color of the sun. Okay. Disadvantages, they are being moved out. We are not using them much anymore because of their low efficacy, because of high operating temperature, the high infrared component, which is not efficient because we do not see the infrared. Okay, short life. Okay, so now let's go to the fluorescent. So now application of incandescent. Okay, so let me jump into fluorescent lamps. Advantages: better efficacy, long life, low brightness, low operating temperature, low infrared output, good color rendition, higher system voltages. We cannot dim the fluorescent. Disadvantages: they require a ballast. Ambient temperature affects them. In cold weather, we cannot turn on those lamps. The luminaires are bulky. A special ballast to dim. Applications: large area general lighting in offices and industrial plants. Now next, the high intensity discharge lamp. Very good efficacies, very long life, high output, compact size, Disadvantages: the color, okay, can be a disadvantage. They are costly. They are very bright. They are difficult to dim. Stroboscopic effects, cold weather. Applications: high bay, interior, industrial applications, outdoor applications, street, parking lot, security. Okay. So I have here a few questions. Let me just discuss a few of them in a moment. Look at question number question 1. Okay, so the answer to 1 is 683, right? What is the luminous efficacy of the perfect light source? 683 lumens per watt. Number 2, list the following lamp types in order of their luminous efficacies from lowest to highest. Okay, so then we can look at the first table. in the first page. And then we will see that, okay, so the mercury lamp is the less, okay. Now another question is 4 and 5. They are related to lamp life. So what's the effect of voltage on lamp life? Okay. High voltage, low voltage. So remember, if we change the voltage, then the current through the lamp is going to be smaller. So then that may help the lamp. However, the voltage cannot be increased very much because of the insulation problem within the lamp. Okay, so you can read and look at the answer to these questions. Then the other question is 11. Why ballast? Two major reasons. Okay, so we said one was to limit the current in the electric discharge. And then the second one is to start the discharge. And then minimizing the stroboscopic effect. So we said using three-phase or currents which are out of phase, so that they do not cross, zero cross at the same time. Okay, so that's just a few of the questions. Let me see if we have something else. Okay, so here we have tables for incandescent lamps. So look at the top, the titles of the rows, no, of the columns, sorry. And then we have the lumens per watt and the LLD. So LLD is the lamp lumen depreciation. So that means that after lumen percent of okay, after 30% of rated life, so after the lamp has been used 30% of its rated life, percent output at, no, the lamp is going to emit less lumens. So that means if the lamp is 1,000 hours, when the lamp has been used 700 hours, 70%, 700 hours, then the lamp will be shining 89% or something like that. So that's the lumen depreciation, lamp lumen depreciation. Okay, now these are fluorescent lamps. Now, look, here, the bulb size and length. So here are the length, 48 inches, 96 inches, 48 inches, that's 4 feet, and then 8 feet, 4 feet, 8 feet, and then T. So what's the T? The T12 is the diameter. So look, if you look at the lamp in the cross section, okay, so here is, so T8, what does it say there? No, T12. T12 means equal to diameter 12 over 8. So that means 1.5 inches. So the T number is the diameter in terms of 1/8 of an inch. Okay? T8 diameter equals 8 divided by 8, 1 inch. T6, now we can see T6, T5, so 6/8, 3/4 inches. So then the bulbs now are slender, so they are more economic, I guess. So that's the T for the diameter. Now, something important again is also the color. The color. So here are a bunch of acronyms. I don't remember now. Initial lumens per lamp, but color is given as lamp temperature. For example, 3000 K in degree. So that means a bright. So for example, for fluorescent white color, 3400 K, 6,000 is the apparent temperature of the sun, T of sun. Okay. So then very bright or 3000, so it's pale or cold white. So that's the color. The lamp temperature. Then what else do we have? The lumens per watt. Okay, look, CW, cool white, WW, warm white, deluxe lamp, super saver. So that's the color. And here we'll see that they are expressed in color temperature, like this, these numbers here. Okay, so then next, again, now these are the mercury, the halide, and the high pressure sodium lamps. So now the lumens per watt, they are higher, especially for the sodium. The lamp lumen depreciation. What else? Greater life. Or fine, very good. Okay, so that's this. Do you have questions regarding this? Okay, so then let me stop share this and take a quick break. Okay, so now what I want to look at is the this. Open this in your computer. Open this software. Okay, so let's look at it. Where is it? Okay, so let me share now the screen. So we want to get this out of the way now. Here. Okay, so this is the program. Okay, visual program. You see it?
Yes.
Yes, we can see it.
Okay. So, for example, if you were to be an engineer with an engineering certification, professional engineer, and then you will be selling projects to the public, then you need this software. So let's look at interior here. So I click on interior. So that's an hypothetical interior space. So we can see some dimensions there. And then in the center is the room, okay, an interior. And then we have the room dimensions, and we are using English units, feet and foot candles. And then this room has 30 feet times 20 times 12. The work plane, so that's the height of the table where the lumens will be rendered. That's the work plane. So that's 2.5 feet above ground. The ceiling type, okay, so ceiling type, well, okay, it says, okay, open. Then the room reflectances. Now, in this designs, the color of the walls are important, okay? So that's why we have those reflectances. All right, so then criteria, constraints, fine. Then on the right-hand side, we have the calculation results. So when we insert an amount of luminaires here, then we will get the luminance in foot candles, the power density in watts per square foot, square, yes. How many lamps, the spacing, okay, fine. So then let's look at the lamps. So now click on the plus sign here on the left. And then this is the the library of lamps according to manufacturers. So I chose Litonia. When I had a business for electrical installations, starting, that was in 1990 to around 2005, I had a business in Mexico, in my hometown, for electrical installations. And I will buy Hall of Fame and Litonia. Okay, so then let's look at this lamp. Litonia linear. See there? We have the data of the lamp. Look, first we have the illuminance distribution, the polar plot. So we can see that all the lumens are directed downwards, okay? Downwards. Next, we have, if you read carefully, you can see that it's going to be 6,000 LM, 6,000 lumens. 80% CRI, that's the color rendition index. 3000 K, that's the color temperature. So this is rather cold, a cold white. The lamp Okay, then we have the lamp itself. So one is the luminaire, including all the housing of the luminaire, the reflector, the reflecting surfaces. One is the luminaire and another is the lamp itself. The lamp is just the bulb, right? 50 watts. Okay, so then select that. And now you can see that the software put 6 lamps on the ceiling of that room. Okay. And then on the right, you can see that the illuminance is 38 foot candles. 38 foot candles. So is that good or not? Well, let's look at the next chapter. So chapter 5, which we will discuss next class, interior spaces. Let's see, we need a table here. Table of lumens. Where would that table be? How many lumens are recommended for interior spaces? So that then we will know if 38 foot candles is good enough or not. Okay, no, I didn't find the table. Well, there were some tables at the start of the chapter. Illuminance categories, it says. Okay, so here we have this. ABC 20 to 200 luxes. Now, these are foot candles, okay? So remember, a foot candle is 10.76 luxes. So if we have 38 times 10 is going to be around 400 luxes. So then that would be DEF. And then DEF is auditoriums, drafting, educational facilities. Look, that's E. Science laboratory, lecture rooms. Okay, so then that goes from, so we said 400 luxes in this calculation. So then it looks like it could be in the range for an educational facility. Okay, how about offices? Offices are higher, so that will not be good for offices. So if you need to increase the number here to get to higher, maybe to 200 foot candles, then you can go and put more lamps. So where are the lamps spacing? Criteria, constraint. How do I put more lamps? Somebody try to put more lamps, maybe 12 lamps instead of 6. Quantity. So let's put in quantity here 12. Wow. Okay. So here are 12, and it didn't grow very much. It only grew to 77 foot candles from 38 to 77. Okay. So now, if you want to become an engineer for this, then of course I am not, and you need to become more efficient to arrive to the perfect solution.
Mostly
Okay.
like Like I think it works better if you change the lumens.
Okay, what do you do?
Change the fixture.
Okay, so move here on this. Now where do I go?
If you get that 1200 lumen. I'm sorry, 12,000.
So this, you mean this?
Yeah, maybe we could try that.
Let's try this, okay. And then select. So let's go back to 6. Okay, good. Taking some time. All right. Well, so this is what we have, huh? But it's very rich. Look, if you go, so this one A, so we have A like that, and now B like this, but B is not rendering anything. Okay, so this is 12,000 lumens, A was 6,000 lumens, okay? So then the lumens is important, you see, because we are not getting the result here, but the lumens are higher intensity lamps. Okay, so then good. So then I was going to show, I want to barely see, look, different types of lamps. For example, let's open Hall of Fame. Industrial, let's look at industrial. Floodlight, okay, let's look at floodlight. Okay, so that's the floodlight. Okay, so let's pick up this one here. Select. Now, it has two color rendering, blue and red. So it takes time to understand what do they mean. Blue says 0 degrees H, and red says 90 degree H. Total luminary lumens, 35,000. Input wattage, 285 watts. So these are high intensity lamps, okay? They have a lot of watts. Okay, and then it says efficiency 99.95%. So that's not the lumen efficiency, it cannot be. So I wonder what type of efficiency is that. Okay, but it's not light, it's not the light efficiency. Fine. All right, so then I'm going to stop sharing this, and then let me share the lectures, and then with that we end the class. Okay. So if we do some type of review of what we've been discussing, we can use this document. So let's start with the light sources. So I go to page 2. So here are lighting fundamentals. And then explain the following concepts. So look, lighting fundamentals. So table 3.1. We have all these quantities, variables, luminous intensity, luminous flux, illuminance. So what is that? So the lumen intensity is the candle, the lumen flux is the lumen, and the illuminance is the lux or foot candle. So that table is right here. Right, this is the table. So at the top, we start with intensity, which is the ability of the source to produce light in a given direction. Candles, the definition of the unit. Next is the flux, which is the total amount of lights. So the flux is measured in lumens. So the lumen is the luminous flux emitted in a solid angle of 1 steradian by 1 candle uniform point. And then we have the relations. Lumen equals candles times steradians. Next, we go to the object where the light is being rendered, and then we call it illumination. So that's the amount of light received, okay? So above is emitted, and now is received in a unit area of surface. So we have a lux or the foot candle. They are equivalent units. So 1 lumen equally distributed over 1 unit area of surface. Then we have luminous excitance and luminance brightness. So they are also lumen per meter squared. Those are luxes. Candles. Okay. So that's here. Then the analyze the steradian. So this beautiful picture, which is very demonstrative of what steradian is, okay? So the steradian is at a distance of 1 foot away from the source, the area on the sphere is also 1 foot square. So that's the definition of a steradian. So you construct an sphere, then mark on the sphere a surface equal to the same radius of r square. So it's going to be the radius square, that surface. And then that angle is the steradian. Okay. Now, we use irradiance for radiometric and luxes for photometric. So one is the problem of radiation, like solar radiation or radiation from radio sources. And the other problem is the problem of illuminance. So this is the difference, okay? Then in chapter 3, again, we discuss those fundamental concepts. Then we look at this software, Acuity brand. Okay. So we are not doing any projects on lighting projects. Next time we are going to discuss chapter 5, lighting systems, layouts for internal spaces. Then 12, let me go to page 12. So again, the candela, the amount of watts emitted in 1 steradian. So 1 lumen is going to be the best case scenario is 1 lumen, 688 watts. Now here in problem 5, for example, it says an incandescent bulb for 100 watts and 1700 lumens. The luminous efficacy is 1700 divided by 100, right? Equals 17. This is for transformers. So let me see. Now let me go to page 16. Okay, we discussed this the last class. So this is like a geometrical, we were calculating here the luxes. So we need to divide 2000 over the distance square. So the distance is, for this lamp 1 is 5, so that's 25. 2000 over 25 is 80 luxes. And then we need to use geometric angles, the cosine for the vertical and the sine for the horizontal. So we discussed these problems here. Now problem 7 is about a room. So we'll discuss this next class. So this is the definition of the different volumes in a room where we have the work plane, the position of the luminaires. So then the room is divided in 3 cavities: the ceiling cavity, the room cavity, and the floor cavity. Okay. And then it indicates also given reflections coefficients, rho W, reflectance from ceiling, reflectance from floor, and then this H, C, H, ceiling cavity, H, room cavity, and H, floor cavity. So this is called the zonal cavity method using 3 cavities. Okay, so this was the old method when there were no computers. So then the design was done with these methods, analytical methods. Now with computers, I think the computer follows a point-by-point calculation. What do I mean by point-by-point calculation? This is what I mean. Let me show you. We just look at that. This is point by point calculation. So the computer divides the space in many, digitalize the space in many points. And then for every of these points, you get a given calculation of luxes. So it's a lot of calculations, many lamps. This is only for 2 lamps. Now the computers can put a lot of lamps in many points and do it in brute force. Before, that was not possible. And they use these methods that we are going to discuss briefly next. All right. One more thing. In homework 1, I made a mistake. So now let me make a correction of mistake. So in homework 1, remember this problem with the capacitor for power factor correction. So the mistake that I made was that I connected the capacitor, I connected it here directly across the inductance. So that's incorrect. The capacitor is, see, this whole resistance inductance would be like the equivalent circuit of a motor, the wiring and the coils of the motor. So then the capacitor is connected across the motor. So these are the motor terminals, and that's where the capacitor is connected. Therefore, for the calculation of voltage, we use 1200 volts, the source voltage. So, okay. Most of you did understand that way because you use 1200 volts. So then I put the correct marking. If you have any comments on this problem in your homework 1, let me know. Okay, so end of class now. So please write your name and class dismiss. If you have any questions, thank you. See you on Monday. Okay. Hold on, I need to break away in a moment.